Hello, everyone. So last time we were looking at the concept of local linear approximation and differentials. So let's remind ourselves. Linear approximation. For a differentiable function let's say f of x close to x equals a. So we can say that f of x is almost equal to f of a plus f prime of a times x minus a. Okay, so this is approximation for f of x if x is close to a. And this equation is the equation of tangent line at x equals a. Okay, so this is equivalently, we saw we can write this as f of x minus f of a almost equal to f prime of a times x minus a. Now this one, we saw that this is differential of y if delta x dx is set as delta x, which is x minus a, and if x is equal to a. And this one is delta y. So dy, differential of y, is an approximation for delta y if we set dx to be delta x and x equals a. Now, what was the definition of a differential? Where differential y is defined as f prime of x dx. Okay, for y equals f of x. So if you have a function y equals f of x, then dy is defined as f prime of x dx. And if you fix the value of x to be a and dx to be delta x, which is x minus a, then dy will be f prime of a times x minus a, the right-hand side of this approximation. And this will be an approximation for the left-hand side, which is basically delta y, difference between y values. Okay, so and we also saw that, error. By error, we mean, error in x, we mean delta x. In y, we mean delta y. Now, there is also a concept of relative error. Relative error, let's say in x, is defined as delta x over x. And similarly, the relative error in y is defined as delta y over y. Okay, so this is the concept of relative error. And now let's look at an example. Let's say, suppose that the diameter of a sphere is measured with percentage error of plus minus 0.4%. Estimate the percentage error in the calculated volume of the sphere. The calculated volume of the sphere Okay, so what do we know? We know that delta x over x. So let's say suppose that let's say x denotes the diameter of the sphere. Then what can we say about the relative error? The relative error, percentage error means relative error given written in percentage. So it means delta x over x is between which values? Between minus 0.4%. So minus 0.4% means minus 0.4 divided by 100, right? And 0.4 which for percent which means 0.4 divided by 100. So that means delta x over x will be between minus 0.004 and 0.004. Okay, now we want to know about the percentage error in calculated volume. So we want to know or want to estimate delta V over V. Okay, so we know the percentage error in measuring the diameter is like, we know it's how much, like 0.4%. And based on this, we want to find the percentage error in measuring the volume. Is it same percentage or is it less or is it more? So that's what we want to figure out. So what is the formula for V? So first, write the equation for V in terms of X. So what do we know? The V volume is 4 over 3 pi r cubed, and r is the radius. And of course, the relation between radius and diameter is that the radius is half of the diameter. So then this is 4 over 3 pi x over 2 to power 3, which is 4 over 8 times 3 times pi times x cubed. And that's pi over 6 x cubed. So this is the formula for V. Now, we want to estimate delta V over V. Now, what does provide an estimation for delta V? Well, dV provides an estimation for delta V. And what is dV? So we know dV is almost equal to delta V. And what else do we know? And we also know that dV is equal to 4 over, pi over 6. X cubed. Derivative times dx. So dV, by the way, dV evaluate dV, where dx is said to be delta x, of course, right? Provides an estimation for delta V. So dV is derivative of this function times dx. So that means dV equals, what is derivative of this function? Pi over 6x cubed. Derivative of x cubed is 3x squared. So 3 pi x squared divided by 6 dx. So this is pi x squared over 2 dx. Now, if we set the dx to be delta x, then dv, when we set dx to be delta x, evaluated for dx equals delta x, will be equal to pi x squared over 2 delta x. Now, dv over v, remember, our goal was to estimate delta v over v, but estimation for delta v over v is dv over v. Now, we already calculated dv this way. Now, dv over v, we just need to divide everything by v. So that's going to be pi x squared over 2 dx divided by v. V is what? Pi over 3 pi x cubed. Now, pi cancels, so we'll get 3 over 2 dx over x. And so delta x over x, the right-hand side, there is delta x. And we already know the range for delta x over x. So we just need to multiply everything by 3/2, right? So we know that delta x over x is between minus 0.004 and 0.004. So if I multiply everything by 3/2, then I'll get multiply by 3/2 minus 0.003. 3/2 delta x over x and 0.003. And this guy here is dv over v. So then we can say that dv over v is between minus 0.003 and 0.003. And this is an estimation for delta v over v. So since dv over v is an estimation, for delta v over v, what can we say? We can say that we can conclude that the relative error in estimating the volume is within 0.3%, right? This is estimation for delta v over v, and our goal was to estimate the relative error in measuring v, which means estimating delta v over v. So this number will be the range for estimation of delta v over v, and so estimation for delta v over v is between minus 0.03% and 0.3%. So we can say that the relative error in estimating the volume is within 0.3%. Okay. All right. So I can include more questions in the assignments, for more questions for this topic. But let's move on to the next topic, which is L'Hopital rule. L'Hopital rule to evaluate indeterminate limits. So far we saw about indeterminate limits, right? In the first chapter, we saw about indeterminate limits. So that, for example, if you have 0 over 0 or infinity over infinity or 0 times infinity or 1 to power infinity, or 0 to power 0, or infinity to power 0, or infinity minus infinity. These are all indeterminate forms. Seems my screen is freezed. Let me stop share. Okay. These are all indeterminate forms. 0 over 0, infinity over infinity, 0 times infinity, 1 to power infinity, 0 to power 0, infinity to power 0, and infinity minus infinity. These are all indeterminate forms, meaning that the answer could be anything potentially, but of course depends on the example and depends on the type of the function. Now, for depending on the function, depending on the example, we have to simplify in order to see what the answer is. So the answer could turn out to be 0 in some cases. It could be 5. It could be -2. Any number. It could be infinity. Or it may not exist. The limit may not exist. So anything can happen. So that's why we are calling them indeterminate forms, because it's not determined that what the answer is. Depends on the example, depends on the type of the function. Now, what was the recipe that we provided in the first chapter to calculate these indeterminate forms? So we saw to evaluate a limit of this form, we can simplify by factorizing or rationalizing right? We can simplify by factorizing or rationalizing the fraction, or if there is a power, we can take log, right? So we saw many examples, but today we want to give a new recipe, a new method to calculate these indeterminate forms, which is actually easier and faster compared to the previous method. So an alternative to evaluate these limits, to evaluate indeterminate limits, is a rule called L'Hopital rule. So theorem, so let me state it as a theorem. So suppose that f of x and g of x are differentiable functions. Differentiable functions, and suppose that limit f of x as x approaches to a equals limit g of x as x approaches to a equals 0. Or limit f of x as x approaches to a equals limit g of x as x approaches to a equals plus or minus infinity. Also, suppose that limit f prime of x over g prime of x as x approaches to a exists, or it is infinity or minus infinity. Then we can say that limit f of x over g of x approaches to a is equal to limit f prime of x over g prime of x as x approaches to a. So the rule above still holds if we replace x approaches to a with x approaches to a from right, or x approaches to a from left, or with x goes to infinity, or x goes to minus infinity. So this the limits that the theorem that we mentioned was for the limits of functions of the form limit f of x over g of x, where x approaches to a. Now, if you replace all x approaches to a with x approaches to a plus, or replace all of them with x approaches to a minus, or replace all of them with x approaches to infinity or x approaches to minus infinity, as long as the conditions of the theorem hold, meaning that, limit f prime over g prime exists or is infinity or minus infinity, and f and g, of course, differentiable functions, then we can still say that this limit f over g is same as limit f prime over g prime. So what does L'Hopital theorem tell us in a nutshell? So in other words, the indeterminate limits, for indeterminate limits of the form 0 over 0 or infinity over infinity to for indeterminates of this form, to evaluate the limit we can differentiate top and bottom. We can differentiate top and bottom separately, and then evaluate the limit, assuming that the resulting limit exists. For other indeterminate forms, if you want to still apply L'Hopital, first change to 0 over 0 or infinity over infinity. So L'Hopital rule is a rule that can be applied not for all indeterminate forms, only for indeterminate form of the form 0 over 0 or infinity over infinity. As I mentioned earlier, there are still more indeterminate forms. 0 over 0 and infinity over infinity is just two of them. We still have 1, 2, 3, 4, 5 more listed here. But L'Hopital rule only for 0 over 0 and infinity over infinity. What about the others? The others, if you want to, for the others, you can use another method if you want. Or if you want to use L'Hopital, first you need to write it in the form 0 over 0 or infinity over infinity. Is that possible? In most cases, yes. It could be a little bit tricky to transform it into one of these two forms. But in most cases, it is possible to write it in one of these two forms. And if not possible, then you can still apply another method to calculate the limit. Okay, so that's one thing that I want to say, that, you know, for applying L'Hopital, be careful that the indeterminate form must be, first of all, you need to have an indeterminate form, right? For example, if you have 5 over 0, 5 over 0 is not indeterminate form, so we cannot apply L'Hopital either, and we don't need it because we know that 5 over 0 plus is plus infinity, 5 over 0 minus is minus infinity. We don't even need L'Hopital because it's not an indeterminate form. So that's the first thing, that which indeterminate forms you need to have to apply L'Hopital. And also, if you want to use L'Hopital, another thing you have to be very careful is that for L'Hopital, we are differentiating top separately and bottom separately. See, we are saying that limit f over g is limit f prime over g prime, which means limit differentiate top and differentiate bottom separately. We are not saying limit f over g the whole prime. We are not applying quotient rule. Okay, we are not applying quotient rule to find the limit. So that's another thing you have to be careful. Because if you want f over g the whole derivative, then we need quotient rule. But L'Hopital theorem does not say that. It does not say that you have to differentiate the whole fraction to calculate the limit. It says simply differentiate top, simply differentiate bottom, then there is you get a new fraction. Limit of this new fraction is same as limit of the original fraction, as long as limit of the new fraction exists. If the limit of new fraction does not exist, or it's not infinity or minus infinity, then we cannot apply L'Hopital. So if I want to summarize the important remarks of L'Hopital rule, so important remarks. 1, apply L'Hopital only for 0 over 0 and infinity over infinity. Second one, to apply L'Hopital do not use the quotient rule. Instead, differentiate top and bottom separately. And the third remark, if limit f prime x over g prime x as x approaches to 8 does not exist and is not plus or minus infinity, then we cannot apply L'Hopital. Because if you want to apply a theorem, always all the conditions of the theorem must be valid, must hold. One of the conditions of this theorem is that limit f prime over g prime must exist, or it should be infinity or minus infinity. Under this condition, then we can say limit of f over g is limit f prime over g prime. But if limit f prime over g prime does not exist, we cannot conclude anything. So it is possible that limit f over g exists, but limit f prime over g prime does not exist. And it's not contrary to this theorem either, because if limit f prime over g prime does not exist, we cannot apply the theorem. Okay, so these are the three important remarks applied only for 0 over 0 or infinity over infinity. Do not use quotient rule, just differentiate top and bottom separately, and make sure that limit f prime over g prime exists before you apply the theorem. So third remark is just, we usually don't pay attention about the third remark much. Only for some tricky questions, we have to pay attention to the third remark. But for straightforward questions, usually just the first two. But for some tricky questions, then we have to pay attention to three. I'll give you the examples. Let's start with a very simple one. Evaluate. Let's say limit x squared minus 5x plus 6 divided by x squared minus 4, x approaches to 2. So what are the functions here? Here f of x is equal to x squared minus 5x plus 6. G of x equals x squared minus 4. Which are both differentiable functions. And the limit is of the form 0 over 0, right? If you replace x with 2, you'll see that top becomes 0, bottom becomes 0. So limit will be 0 over 0. And what else? So limit, then let's check limit f prime over g prime. If limit f prime over g prime exists, because the limit is of the form 0 over 0, then we can say that the original limit f over g also exists and is equal to limit f prime over g prime. So now check, now to apply L'Hopital, check limit f prime of x over g prime of x as x approaches to 2. How much is that going to be? F prime of x over g prime of x, x approaches to 2. So differentiate top and bottom separately. The derivative of top is 2x minus 5. Derivative of bottom is 2x. X approaches to 2. So then this is 4 minus 5 divided by 4 minus 1 over 4. Thus, by L'Hopital rule, limit f of x over g of x as x approaches to 2 exists and is minus 1 over 4. Okay, so limit, we wanted the question asked us to calculate limit f over g. First, we checked whether it's determinate or indeterminate form. Well, it was indeterminate. And what type of indeterminate? 0 over 0. It's indeterminate and it's 0 over 0 and the functions are differentiable. So let's calculate limit f prime over g prime. If this limit f prime over g prime exists, then we can say the original limit f over g also exists and is equal to the same number. So limit f prime over g prime is derivative of top of limit derivative of top over derivative of bottom was minus 1. It turned out to be minus 1 over 4. So if limit f prime over g prime is minus 1 over 4, and the limit is of the form 0 over 0, then we can say that the original limit exists and is equal to the same number, which is what we wanted to do. So from L'Hopital rule, we concluded that the original limit exists and is equal to minus 1 over 4. So verify our answer using the method you learned in chapter 1. So this is the new method, but you already know one method. The method of factorizing, we can easily factorize this and calculate the limit. Do that and check that the answer must be minus 1 over 4. So let's look at the next example. Let's say limit x squared, this time minus 5x plus 5 divided by x squared minus 4. X approaches to 2 from right. So the very first step we can do is that to determine whether the limit is indeterminate or determinate. So let's first do that. If I replace x with 2, what do I get? So 2 squared minus 5 times 2 plus 5 divided by 2 squared minus 4. So this is 4 plus 5, 9 minus 10 minus 1 over 0. So this is not indeterminate. This is determinate. So if it's not indeterminate, we don't need to do anything. We don't need to apply L'Hopital or any other method. Just follow the rule that we mentioned for determinate forms. Determinate forms we explained before in chapter 1, that how we can find out about the answer. We said if there is a constant, non-zero constant over 0, then the answer is always infinity or minus infinity. This is determinate form. Answer will be infinity or minus infinity, depending on the signs of top and bottom. So let's see whether the signs, so limit x squared minus 5x plus 5 divided by x squared minus 4. X approaches to 2 from right. So this is 2 plus squared minus 5 times 2 plus 5 divided by 2 plus squared minus 4. The answer is minus 1 over 0 plus. The top is minus 1. 4 plus 5, 9 minus 10 is minus 1. The bottom is 0 plus. Why is it 0 plus? Because see, if x 2 plus means what? 2 plus means x is the value of x is a little bit bigger than 2, right? So if x is a little bit bigger than 2, then x squared will be bigger than 4. And so x squared minus 4 will be bigger than 0. So that's why we have 0 plus. So we wrote 0 plus. 2 plus means x bigger than 2. So x squared bigger than 4. X squared minus 4 will be bigger than 0. And something bigger than 0 can be denoted by 0 plus. And minus 1 over 0 plus is minus infinity. So top is negative, bottom is positive, so the answer is minus infinity. So we can say that limit x squared minus 5x plus 5 divided by x squared minus 4 x approaches to 2 plus is equal to minus infinity. So it's not indeterminate. We don't need L'Hopital. We would need L'Hopital if there is an indeterminate form. And we are only allowed to use L'Hopital not for all indeterminate forms, only for indeterminate form which are of the form 0 over 0 or infinity over infinity. For other indeterminate forms, first we need to transform them to one of these form, either 0 over 0 or infinity over infinity. Okay, I'll give you more examples. But before that, I just realized that for the beginning of the lecture, the example we did for relative error, I made some calculational mistakes. So here, when we divided dv over v in terms of x was pi over 6x cubed. I derived the formula here. So I made a mistake here, 4 over 3 pi r squared, but in terms of x, we saw is pi over 6 x cubed, right? In terms of x, v is pi over 6 x cubed. So instead of the constant in front will be 3, not 3/2. It will be 3. So I just need to change every 3/2 here with 3. The multiplying factor will be 3. And then this will be 12. And this will be 12. Here also 12 and 12. And 0.012 means how many percent? If you want to write in percent, means 1.2%. So the estimating of volume will be within 1.2%. So yeah, I just want to mention that, I made a calculation mistake because for the formula for v in terms of x was pi over 6x cubed. So instead of 3/2 times delta x over x, which is what I wrote before, the correct multiplying factor will be 3 times delta x over x. So everything had to be multiplied by 3, and we got these numbers. Okay, so we're going to give you some more examples of L'Hopital rule to see how we can handle indeterminate forms and calculate the limits using L'Hopital rule.